And so welcome again, everyone, to this July event. And I'll pass the word to my colleague, Rafaela Ribeiro. And I look forward to this fabulous event. Thank you.
Hello, everyone. It's a pleasure to have you all here. Today, our Ladies Room presents Forecasting Time Series with Linear Regression, a feature-driven approach. And we have here Rami Krispin. Wait. Okay, a disclaimer. This talk is recorded and will be posted on our YouTube. Please remember that all our attendees are expected to adhere our code of conduct. We ensure a safe, inclusive, harassment-free space for learning. We are committed to providing a respectful environment where everyone feels welcome to learn, connect, and grow. Who we are. We are Our Ladies, a local chapter of Our Ladies Global dedicated to promoting a continuous learning in the open source community. Our monthly meetings provide a platform to discuss current trends and hot topics such as Git and Python as well. So join us. If you would like to join our team and contribute to our community, we have a few open positions. So fill out the form if you have some interest. Our next event in July, the Our Ladies presents Visualize Data Per Eye Peasantry by Rita Giordano. Event in Italy for healthcare professionals focusing on data visualization for patient care. So today, without further ado, Our Ladies presents Rami Krispin to Our Ladies Room. Rami leads the data science and engineer team of Apple Finance Services in Infra, where he helps transform complex business questions into data-driven solutions using machine learning and statistical modeling. He is also open source computer and author of hands-on time series analysis with R. Today, he is joining us to share practical insights on feature-driven time series forecasting using linear regression. Please give us a warm welcome to Rami Krispin.
Thank you, Rafaela, for the introduction. Thank you, everyone, for joining and for the invite. Generally, I present a lot, but I don't remember when was the last time I presented on forecasting with regression, and that's probably my favorite topic, so I'm super excited to talk about it. Let me go ahead and share my screen. I shared the materials on the chat, so if you want, you can find it. Now we'll talk a little bit about how to use this repository if you want to follow along. Okay. All right. So generally, we have a light slide today and mainly quarter docs with a lot of examples. So it's going to be heavy applied coding, and I think the audience here probably would prefer this than talking about theory. So you already introduced me, but generally a little bit of myself. As mentioned, I'm working at Apple. I'm not representing today Apple in this talk. I love time series. I love MLOps. Focusing the two things that I typically write about is either time series or Docker and MLOps. I have a newsletter that I write every week about the resources for data science. So feel free to subscribe. It is on LinkedIn, or there is also Substack version. And generally, I'm working on another newsletter for forecasting, so that's sometimes in the future. And you can find me on on this QR code. All right, so we have a packed agenda. We have 2 hours. I hope we can have all the content I plan to share today. But if not, the notebooks are there, and I try to a little bit write some explanation about how to use them. So we start by we'll go over the repo and understand if you want to use it, what do you need? And then we'll go to descriptive analysis of time series, which is critical for feature engineering. We'll see like the common methods for understanding your data, and based on this, you can make a decision what type of features you want to create. And then we'll go and apply those features, build those features, and see how they impact models. I try to include what I think is important. Definitely, there are other approaches. And so take into account the limitation of time. We have only 2 hours, so we cannot cover all, but at least we'll give you a flavor of how you can use linear regression, or when should you use linear regression. And you can then explore further if it's something that apply to your day-to-day work. Generally, linear regression, if you understand linear regression, then you can apply, it's the engine. You can replace it with any other machine learning models, such as XGBoost or Ridge, Lasso, and so on. So the principle will apply to any other regression method. And the materials are available in this repository. I shared it on the chat, and let's just go and check this repository, and I will walk you through the settings or what I'm using. And there are a couple of options if you want to run it, how to approach it. So we'll open my VS Code. Let's just close all the tabs and start from, there is a lot of tabs. So just if you didn't use VS Code and if you're using RStudio, it's different, right? So anything I'm doing now, you can use with RStudio. I moved to VS Code. Let's close all of it. I moved, start to use VS Code because of Docker. VS Code provide a native support to Docker, and this is a completely different topic, but it enables a high level of reproducibility, and I'm using the dev container extension. So if you're using VS Code and you have dev container, you can just open it and it should work. You have here the setting file, and maybe I just increase the font because for people to follow. So if you open and you have the settings, the idea is that everybody can reproduce it if you're using Docker. Now, however, not most people don't use Docker. So the alternative, if you're using RStudio or Positron, is to just open it there and install the packages. The list of packages I'm using can be found under the Docker folder settings files, and there is a JSON file with the list of packages. As you can see, those are the most common libraries, like dplyr, ggplot, Shiny, which I'm not using it today, Plotly, and then there's some couple of packages that supporting time series analysis, Tibble, FastES, and Fibble. I think to run, if you want to run it locally without container, you need to have those. DI API, you don't need. I'm using it to pull the data, but the data that we were going to use already saved under the data folder. So you don't need to have it to run it. If you want to reproduce the data, so then you need to have both the library and API key to access the API, which is free and available. But generally, you can skip it because the data is under the data folder saved as our data object. So in terms of structure, I think the most important is there are 5 different notebooks that we're going to use today, or 4. The first one is the data. It's just if you want to reproduce the data and see how I pull the data, you can use this Quarto doc. And then the second one is going to focus on decomposition of time series data. The third one is correlation analysis. The fourth one is seasonal analysis, and the last one is the forecasting component. So those are the one that you will need. If you want, you have already rendered, it's rendered. So for example, I will open the HTML file, and you can, if you just open it as the HTML file, you can see the notebook rendered as HTML. If you have any questions at any time, please stop and ask. I know Rafaela, Federica, if you want to moderate, I cannot see the chat while I'm in full screen. So let's make it interactive. It's very hard to do virtual events that I'm speaking to a monitor and I'm not sure if people are there. So how about we start and talk about the data, and then we'll dive into the descriptive analysis. So let me open the HTML and let me resize it. I think does the font is okay, the size?
Yeah, it looks fine. Great.
Okay, so what we're going to use today is the data. We're going to use energy data from the EI API. So the EI API is a great resource for time series data. Is US Energy Information Administration. It is part of the Bureau of Statistics, and what they're doing, they are collecting data about the energy fields from the United States. And generally, they have more than 1 million time series data. You can access it via the API. It's very friendly. And if you are looking for fun time series, I suggest checking it. They have all sorts of type of time series from yearly to hourly. There is a lot of examples, like it's a real life example that if you are looking, that's a good place to start. Today, we're going to focus on natural gas, the time series. And we're going to pull, I pulled 3 time series, but we're going to use only 2. I was greedy at the beginning. I thought we'll have enough time also to do like hourly time series, but I feel like it will be too much, but it's already here. So if you want to look at it, but generally the first time series we're going to use as example is the number of natural gas consumers in California. And the second one is the US monthly demand for natural gas. So to pull this time series, I used this EI API. I created this library as a wrapper for the APIs to enable pull data seamlessly. And we're going to use the Tibble library. So I will maybe pause here and explain what is the Tibble library. If you are familiar with R, base R or stats library, R is a backed-in time series object. which called TS. And the TS object is something that exists from the early days of R, and it has a lot of limitation. The first limitation is that when you store the index of the time series, so time series, the definition of time series is a vector of 2 dimensions, the data and the time. And when we say time series, we refer to regular time series, which means that it's equally spaced over time. And the index of time series object use two components to store the index. So if you have a monthly data, you can store the year and the month. And the year would be the cycle, and the month would represent the frequency. Right? So you have a repetitive 12 months, and this is the frequency of the series. This was something that was useful at the time that people used to have a monthly time series or quarterly, but over time, as time passed by, and we started to collect more in a more robust manner time series with the sensors, the amount of time series that we have today exceed our capability to process. That's one thing, and also the granularity. So think if you have hourly time series and you can only store 2 components of the time, then you cannot use TS object because the limitation, you can only use the year, for example, and the hour, but you're losing the day and the day of the year, right? So this is where the table object came as a result. That is a table with a time awareness. So it's a data frame, and you can have regular time, date and time objects to store the index of the series, with the caveats that there is some unique definition for monthly, weekly, and quarterly, which we'll review. So that's just a brief historical about time series object in R. We're going to use the table, which is a more robust data frame, which is easy to work like it's in the tidyverse environment. I'm loading the EI API, so it's stored as an environment variable, and then I'm calling the series. So the nice thing about the EI API that it comes with a dashboard that you can filter the data, and then once you filter the data, so if I cannot open it. Yes, I can. So if you open, it's open the notebook. So if I open this one, let's see, it will open the dashboard with the series with the filter that I use, and you can see the schema of the time series. So you can see we are filtering for consumption of natural gas, bigger font, and then we selected, there are a couple of options, but we selected the number of natural gas consumers, and then we applied some filters. So you can see you can filter, you can get it at a state level. I think we looked at California. Yes. And based on the filters, you get the schema, the header of the request, and I'm feeding it to the function. So going back over here, and all right. We try to reopen the So I'm feeding the schema, and the most important thing is the facets, is like the filters that we're using. So we are pulling to data for California, and the process is consumers, number of consumers. And so that's the code for this series. And then we don't use define the start and end. We want to call the whole series. And we need to define the path. So think about it we want to pull, there is a hierarchy, so we want to pull natural gas, it's a consumer data, and then it's the number of consumers. So it goes well with kind of like the filters that they're out over here. And once we pull it, you can see we get a time series or table. We have a lot of fields, but for us, what we care about is the index. We have a yearly time series, and we have the value. Where are the values hiding? Somewhere here. The value, and that's what we need. So we'll take the time series, the table, and convert it into a T-civil object. So we'll rename the name of the index from period to index. We rename the value column to Y. And the only thing we need to define in this case is what we are using for index the series. And you can see we got a table, which looks like table, but then you can see that it's indicate the frequency of the series and its yearly data. So you see the index is the year, Y is the corresponding observation, and this is just a code for the reference. And if we plot it, you can see a nice time series. One thing to note that this is like I left it just to show like this is something you will probably see if you're working with time series, that the first observation looks weird, which is normal. Maybe this is the time they start to track this KPI, and then it took them a year, or maybe there was another reason, like I don't know, but like typically you'll see like that sometimes the data collection was not in place, and then you will see this weird. So obviously we will remove it, but just left it just to show like kind of like not always you get a nice academic time series, although this is really nice time series data. And you can see that if we zoom in, you will see different patterns, right? So now you can see it's nicer, like you can see how it goes, there is some change in the structure of the trend over here, and we'll dive into it when we look at patterns. The next time series that we're going to use is US monthly demand for natural gas, which is very beautiful time series. Repeating the same process to pull the data, and we'll convert and reformat it to a TIS object. And this is the time series. Here you see a different structure, right? You see the seasonality, high usage during the winter time. In the United States, some states that are cold in the winter, they're using natural gas for heating systems. It's very common in the United States. So you will see that increase in the consumption during the winter time, and then toward the summer, it's dropping down, and there is an uptick. Maybe there is a consumption for producing electricity during the summer. So that's why you see because of the AC. So it's very structured, right? It's very repetitive and a nice time series with a nice trend. The third one we're not going to use, but if you want example for hourly, so this is the demand for electricity, hourly demand for electricity in California for subregion PG&E. So this is where I live in California. I'm using PG&E as it's my provider for electricity. If you are in California, so people have a mixed feeling for this company. They're increasing the price all the time. And that's how a nice hourly time series looks. And one comment, the reason I'm using Plotly, interactive data visualization, non-interactive like ggplot, is it's very convenient when you want to dive in time series like this and zoom in to do something like this and look at the data fast, right? So it's very convenient to look at the pattern. the nice thing about here that you have the patterns that you have here is the strong seasonality. It's the hour of the day and the day of the week, right? Probably on the weekend, people consume more. And then you have the month, right? Winter versus summer and so on, cycles. We're not going to use it, but it's if you want to explore hourly time series, so definitely recommend checking this API. I'll pause here, see if there are any questions on the data. Okay, let's open the second notebook. You know what? We will open both the HTML and we'll run it side by side because I think there is some added value about. And this is what annoying in VS Code compared to RStudio. You need to open terminal. It's a really do-it-yourself thing, for good and for worse. And I will open our instant. And let's split the screen. And let's close this so we have more space. And also let's open the rendered format. It would be nicer to, oops. Okay. So I will start with this one and go explain what is this decomposition. And the reason I'm starting with decomposition, because I think this is one of the best approaches for exploring time series that give you, with minimum effort, maximum information about your series. And this is one of the first things I do when I explore time series. I'm running decomposition. So decomposition, as the name implies, is taking a series and break it down. And we're breaking down to 3 components: trend, seasonal, and irregular. And generally in time series, you will see that it is very common that either you will have or don't have trend and seasonal, right, components. And so those are the most common components in time series. You will either have one of those at least, unless you have a very flat line, right? If it's not flat, it's there you have some trend. And if it's a oscillate based on the periodicity of the time series, you have seasonality. And we want to understand, because this is how we can understand what features we want to build. So we want to understand if those patterns exist. And the irregular pattern is anything that is not represented by trend and seasonal component. And this is important because in most cases in life, unless you're really lucky, your time series in real life will have more components that are not backed in the seasonal or trend, or either that just the trend or seasonal components doesn't capture them well. And the way to think about it is in some cases it's called the remainder. Any patterns that is not part of the trend and seasonal component estimation. And I will talk a little bit more toward the end of this about how to look at the irregular. Generally, if your irregular component is a white noise, meaning that it doesn't have any correlation, so you capture all the information from the trend in the seasonal component. That's the ideal. In reality, you may see that some cases it's not. You have some correlation left in the irregular, and then you want to explore it. So there are many methods, but there are 2 that are common to decompose a time series data. There is the classical decomposition and the STL. And we're going to review the classical rule. It's very simple. I will just review how to do it. And and then we will move to the STL and understand what are the differences between the two. So,
sorry,
yes.
Rami, we have a quick question by Debbie. Are irregular patterns also outliers?
Yes. So again, I can give example for what could be left over that is not part of the seasonal and the trend. So one thing is could be outliers, right? So you have some abnormal in your data that is not part of those two components. Then you can have a structural break. You can have those structural breaks should be captured by the trend. You can have recurring events that are non-seasonal in their nature. So think about the difference between if you're looking, for example, on sales data, holidays that are impacting the sales, if you have products that are being impacted by sales. So Christmas, every year, it's in the same date. It's in the eve is in December 24, and the Christmas day is 25. But there are some holidays that are the date is fluctuate every year. So let me find one. So Chinese New Year Eve is every year is in a different date. It could be somewhere between January and February, if I'm not mistaken. So if you are selling in China and you want to model it, you will see that this is moving, and then like it's confusing the seasonal component because it's not at the same date, but it's repeated every year. So this is an example for another reoccurring but non-seasonal events that the seasonal component cannot capture. Yes, I think those are the one, and we're going to look at those one. So we're going to, so how do you do this decomposition, classical decomposition? We load the time series with the seasonal component, the second one, the demand for natural gas. It's a good example. And now we talk about classical decomposition. So the nice thing about R is that for any statistical method, you will have the function that's supported on the stats library. So the stats library has the decompose function. And then the Fibble or the FastTS library from Rob Heinemann as a wrapper supporting the Fibble object, and it's called classical decomposition. And we're going to use this one because just because it's supporting the Fibble object, but it's basically a wrapper on top of the decompose function. So it's a multiple steps process to calculate the components of the time series. So we start with estimate the trend component by using smoothing method. So smoothing method, you are removing the fluctuation by calculating moving average, and that's compress the seasonal component and leave you with a pure trend. There are a few methods to do it. The implementation of the smoothing method on the decompose and the classical decompose function is using a centered moving average, meaning that if you are looking for calculate the smooth value for observation at time t to estimate, you will take the previous 6 observation and the next 6 observation if you are looking at a frequency of 12 or monthly, right? If you have a different frequency, you will just take the frequency, and in the middle, you will take the previous frequency divided by 2 and the next frequency divided by 2. So let's say that if you have quarterly data, so you have frequency of 4, you will calculate the average of the current quarter. You take the previous 2 and the next 2 and divide it by 4. So you get kind of like, that's how you smooth the oscillation. Once you calculate the trend, you detrend the series. You are reducing, you are subtracting from the series the trend, and essentially you are leaving the series with just the seasonal component. And you are, if you are trending up, you are just flattening it to be flat, but you still have the seasonality and the irregularity. And once you detrend the series, and maybe before, there are two types of models for decomposition with the classical decomposition. One is the additive. I'm not sure how to pronounce it. Additive model, which is just saying that your time series is linear like is growing in a linear fashion, right? So if you're moving from time t to time t plus 1, you're growing in a constant amount, where if your series is multiplicative, meaning that when you're moving from time t to time t plus 1, you are growing in exponential rate. So in this case, you can either apply some log transformation, or you're just doing dividing instead of subtracting, right? So that's how you detrend the series. And once you detrend the series, you estimate the seasonal component by calculate for each period the average. So if I detrend this series, I take all the Januaries. Let's say that I have 20 Januaries. I take the values of the Januaries, I group them together, and divide it by the number of observations for January. So I get average. And then I will do it for February and so on. So I'm getting estimate for each month of the year, what is the average effect of the seasonality after I remove the trend. And once I have essentially estimated trend and this is a component, I subtract those components from the time series, and I get the irregular component, which is noted as IT. And again, if you are in a case of multiplicative model, you have just divided the multiplication of the trend and the seasonal component. I'll pause here for any questions.
Okay, I don't know. There are a couple of questions in the chat. Okay, one is was earlier. Could this time series decomposition also be achieved by wavelets transform? And the second question is how to know and decide additive and multiplicative model for a given data?
Let's start with the first. If I understand correctly, the question if we want to use weighted average for calculating the seasonality. I hope I'm interrupting the question correctly. So that's the next. The STL is doing this, is weighted average of the seasonal component, which we'll talk in a second why you want to do it as opposed to the classical method of averaging, and we'll see the difference. And then the second question, how to identify so generally, the easy way is to eyeball the series, right? So you can see that you're moving in a constant rate. You can do some summary statistic and calculate growth and see if your growth is component or constant. There's two ways that I think to do it, and then you can try to do some transformation. So transformation will inverse the growth, the exponential growth to regular growth or constant growth. So, right, so those are the methods typically people are using. And there is a most common method to do it with box-Cox transformation. So if someone wants to have more question about it, I can show a good resource to look at it in a second. I hope this has answered the questions. So once we get the estimate of the irregular, so we broke down the series into the 3 components and we can plot it, right? So we will use the classical decomposition function, and we're going to define it as a DTV series. So this function is from the Fibel tools, the model, and then the model itself is from the FastTS. Right, so those are the libraries that I'm using here. And once I'm calculating, I'm getting objects, but I want to extract the components. I'm using the component functions, and that's what I'm getting. So you can see here the model is breaking down into the trend, seasonal, and random, and you get the corresponding columns. See, there are, so you have the seasonal and the seasonal adjust. Seasonal adjust is just removing from the series the seasonality and getting it with the trend. So there is a backed-in function on the Fibel to plot. I prefer to plot it for a variety of reasons with Plotly. So I'm running this code where I'm using Plotly, and essentially I'm plotting each component. So starting with the series, the trend, the seasonal adjustment, the irregular, and then I just subplot them together. I have a backed-in, I will show later, I created a wrapper for this, and you have a function that you can use to do it. But there are some couple of advantages of using it this way. So you can see this is where we started. This is our actual, and I see that I have a typo over here, so it's not actual, it's actual, but you get the gist. And then this is the trend series. So you see after the smoothing, we get it without the oscillation of the seasonality. And then once we subtract and calculate the average, we get the seasonal component. So you see it's constant, right? So no matter where you look across the time series, it will have, for every January, we'll have the same value. In this case, 751,000 observation. And if I go over here, it's the same. So it's a constant per period. And this is just a series if we are removing the serial component from the series and keep it with the trend. So this is a common approach in economic to get the seasonal adjustment. So for example, if you're looking at your sales in Christmas, they are higher compared to a regular month. But if you remove the Christmas impact of the year, are you still higher compared to previous years or not? I think that's usually why the motivation to do it, right? So you want to measure growth. And then you have the irregular. Now you can see definitely, and that's what going to the question about outliers, right? So let's see, you have outlier here, you have outlier here, and one of the downside of this, that if your time series has some outliers, it's average it, and you will get, as every average, you get it in the middle. So in some cases, you will be, okay, but other cases, you will either be lower or higher. And so that's something to be aware, and this is the downside of this method. And going back with this, so this is where STL decomposition solve this issue. So the seasonal and trend decomposition using a loss method is alternative and robust approach to decompose time series data, where it can handle the change in seasonality over time, right? So it's using a weighted window to calculate the seasonal component. So then you can control the size of the window and define if the seasonality, let's say in 2002, is not the same as maybe as seasonality in 25, right? So almost 25 years ago. So you want to make it as a local calculation of the seasonality. So we'll see the implementation again. I'm using the Tibble, the FastES library, and I'm using this model over here. I can define the window that I want to use, how many periods to calculate the trend, local trend, and the window for the seasonality. And I'm getting the same type of object. The naming is a little bit different. I think here it's called remainder to the irregular, and before it was random. And then we get this, it's called season year. So that's a seasonal component, and season adjusted, the adjusted seasonality. So we do the same and we plot it. And here you can see that the fluctuation in the seasonal component is different, and it's more reflect the seasonality at that given period. And again, like we can manipulate it by defining the window size. So that's more how you are familiar with the time series and make this decision. Or you can leave it like as a default, and I believe that it's calculated like 2 cycles. Like if we have a monthly, so we'll take 2 years as a default. And here you see like it's more close to overall to the 0, and then you have the outliers are much more clear. So you still have outliers, but now it's easier to find them. And why I'm telling you about and spending so much time about it, because when you are doing feature engineering for time series and decide how to model, the irregular component is a gold mine. It can tell you a lot about what other features you want to build. And let's take what I like to do is to calculate the standard deviations of the irregular component and mark it between 2 to -2, 3 to -3, and everything above or below 3. So I will skip the calculation. It's straightforward. I'm calculating standard deviation for 3 and 2, and I'm adding it back to the series. So one thing that you can see that now I can think about where are the observations that I actually should be worried about. It could be, somewhere between the 2 and 3, and be more worried about when it's completely out of the 3. And I'm mapping it back to the series. So now I can actually start to think, is the spike here, it doesn't look like it's look normal, but maybe it's not that normal, right? This is very helpful when you are sitting with your stakeholders and you're trying to understand the series, and instead of eyeballing where you have abnormally in your data, is to mark those anomalies and then start the conversation there. Now, like every statistical method, it might be not always right or off, but it gives you a good indication. So that's something we'll use, but definitely you can see that here we have an outlier, and those are somewhere between the outliers, like they're not as significant as this one, but it's nice to be able to see those right away. Any question about decomposition? And let's open the next one. And the next one is also important. It's correlation. So why correlation is important? The easy and more intuitive way to think about correlation in time series is to think about the current temperature. It's not that far away from the temperature in the previous hour, right? So if you want to understand what will be the temperature in the next hour, it should be very close to the temperature in this hour, right? In most cases, right, there are always going to be anomalies like rapid change if you're in the Arctic in the temperature, but like in normal places in planet Earth, the past observation can really tell you about what will be the future observation because they are correlated. And in time series, it's very common that you will have correlation between the series and its past legs. And this is where the autocorrelation function is one of the most common tools to map this correlation or this type of behavior in your time series. And essentially what it does, it calculates correlation with time awareness with the past legs. So it's taking the effect of the how far the time series with the, like if you're taking time series and the relationship with the legs of the series and how far as you're moving on time, obviously there is a time impact. And its factor it is also, as opposed to Pearson correlation, which doesn't take into account the time. So let's take a look at this time series, and obviously we will remove the first observation. And obviously you can see there is no seasonality here, right? So that's one thing to, when you look at it, there is no much of seasonality and there is just nice trend. And we will use the ACF function. So again, like this is something you have in best R, you will have ACF function with lowercase or stats library, and then on the FastDS you will have the ACF function, a wrapper on top of it supporting civil object. So we calculate the ACF score. So we calculate the corresponding correlation of the series at leg 1 and give you the value, and leg 2 and so on. And then we will plot it. I also added the calculation. To the calculation, I added the confidence interval. So we will use, this is a simple calculation. We'll use a 95 confidence interval. And essentially what the confidence interval indicate that if your value is below this threshold, you can ignore it. It's as good as 0, right? And what you see, and this is how typically you will identify that you have a trend, is that you have high correlation with most recent legs. So this is the correlation of 0.91 with the series with the first leg. We're just saying that the leg 1 can expand about 90% of the variation of the current time series, and this is very powerful from predictive power. And then if you go to the second leg, it starts to decay and it's 83 and so on. And this is very common. If you don't see the time series and I look only on the ACF plot, I can tell you this is a series with trend. Now there are advanced applications if you're doing modeling with ARIMA, is to identify the order of the ARIMA. We are not going to talk today on ARIMA, but that's something to know that's very useful if you're modeling using ARIMA models, which essentially is a regression of the series with its legs. So we use the ACF and the partial autocorrelation function to identify the order. So that's like first takeaway. If your structure is like this, you probably want to regress your series with leg 1. Is essentially it's a ARIMA model with a autoregressor process over 1. And then if you look at the monthly time series and repeat the same process, now you start to see a different behavior, and this is because we have a strong seasonality. So you can see still like you have on leg 1, it's high, it's a 0.8, but if you go to the seasonal leg 12, the first one is close to 90. It's expanding more than leg 1. And this is, when you look at it, yes, there is high seasonality in this time series. And if I need to make decision about what legs I want to regress my series, it would be leg 1, leg 12, maybe leg 24, and so on. And I like to add some colors. So I created this function, and I can add as an input the seasonal component. So it's give you immediately, if you want to highlight this is if to see seasonality, it's marked in red the seasonal legs. So 12, 24, 36, and so on, assuming that your time series is monthly. Another way to identify correlation is to use legs plots. I'll go quickly. What I'm doing here, I have this function that I created really fast with ChatGPT. And what it does, it regress the series with some leg. So you can define, I want to regress the series with leg 1, and it's give you this output, right? So I'm regressing the time series with leg 1, and this is the first time series, so it's a very linear. We saw that leg 1 has a significant relationship with the series, and you can see it in a different manner, right? So I'm regressing the series against leg 1, and I'm fitting this linear line. And you can see that I have a nice adjusted R square, which is saying that it can expand a lot of the variation in the series by using this leg. And this is just the formula. And this is like, you can see the same thing for the series. Like if I go to a different leg, like as far, you can see it now still has some predictive power, but it's not as leg 1. And it's really go side by side with the ACF results that we saw in the plot. And then if you do for the second time series with the seasonal component, you can see that seasonal 1 as compared to the previous regression has a lower adjusted R square. But if you go to the seasonal leg, it jumped from 0.65 to 0.91, and it's a better fit. Just telling you, yes, there is a good predictive power in leg 12 for this series. I will see before moving to the seasonality if there are any other questions. And by the way, all the code is here, right? So if you want to see the code and run it, you will have it in the notebook. I think I just think running it line by line on this will have it's less visible than looking at it in the notebook. So let's go to the last descriptive method. So we saw that we can identify seasonality from just looking at the ACF, but you want also to plot it and kind of like feel it and understand more like these patterns. And generally seasonality could be bucketed into the following 3 buckets. Either your time series doesn't have any seasonal component, like the first time series that we reviewed before has only a trend, doesn't have any seasonal, so you don't need to model it. Then you might have a single seasonal component, like the natural gas, And it's very typical to have a single seasonal component when you have a time series of a quarterly or monthly. And then you may have more complex time series with multiple seasonal components. So if you remember the hourly time series data that we reviewed in the first notebook, you will have multiple seasonal components. You will have the hourly, right? So if you take a cycle of 24 hours, people consuming more electricity during the daytime, and then as you're probably getting to midnight, you're going to sleep until the morning, you're consuming really less electricity, and this is a daily pattern that related to the hour of the day. Likewise, people, if you look at the span of the day of the week, people consume more on the weekend days with respect to the regular days because they're spending more time at their homes if you are only looking at residential consumption or demand. And then you will have cycles within the year that might relate to the month of the year and so on. So we're going to focus only on single seasonality, but more or less you can use the same approach to look at more complex. So a simple way to look at seasonal component to plot it is to create a seasonal plot, which is essentially we stack the time series by the cycle. So if we pause for a second, define what is a cycle, there are a couple of definition time series. When I say cycle, I refer to the complete period time of the frequency, and I will break it down. So if you have a monthly time series, the frequency is 12, so we have 12 months, and a full cycle is a year. So we'll stack it by the year. And then you can see over year, and you align every month on the same, under the same x-axis value. So you can compare if year over year you are growing or you're not, or is it, if you see some spike, is it a one time or is it every year you have this spike? So if you take the time series and you are adding a year feature, right? So you're calculating from the date object, the year and the month, and then you just loop over the years and add it, each year representing a line. So you can see this is the most recent year, 2025, and then you have the previous year, and I use a gradient color just to show like moving from as it's more yellowish, it's more far back in history, and then most recent one is a dark blue. Now you want maybe to zoom in so you can see if I'm comparing the last 2 years. That's something that sometimes in time series, in the business context, you can see if your series in the current year is going below the past year, so it means that you have some change in your growth, and if you are like selling products, you should be worried, right? So if your February, so it is or March, we consume less than previous year, so it means it's just like it could be within the, it's not statistically significant, but also it could be that you are having change in your trend. So that's something to think about. And you can add more years, and it seems like it's very complex. If you look at the recent years, they are very close, so should be normal, and it's probably the fluctuation is derived by growth, but also by weather patterns. So probably if you are in years that the weather was colder, so I remember this year I started to study in Michigan, and it was very cold. There was one day minus 40 Celsius, and you can see this is one of the years that was a high record on consumption of gas in the US because of this year was particularly colder than other years. So it's 2014 is very close to 2023. So that's the simple. There are other methods, like think about like you can break it down in different ways, and there is a good read about and I recommend checking Rob Inman book. He has a whole chapter about seasonal plot with different methods. I think that for patterns, I think the previous methods will give you enough information, but always nice to look also on this type of plotting. So with that, we now getting to the fun part. To start use regression. And how about I will actually try to run the code line by line, and if needed, let's render it also. Okay, so if we need, we can go and look over here, but let's run the code just to make it a little bit more interactive. Okay, maybe I can increase the font. And
we have a couple of questions. I don't know if you
yes, sure.
Want to see if you can answer them now, or maybe just postpone it till later on. One is, don't we need stationarity checks?
Yes, if you are using a RIMA. That's the nice thing about regression, that you don't necessarily, you will stationary it, and I will have example how you will make it stationary. Okay.
And another one is there a way to compute many correlations on multiple time series in order to find those time series that have a value that signifies seasonality? I have faced such as an issue trying to predict product sales.
So
compute many correlation on multiple time series.
So generally, so the question, if I understand correctly, there are two ways to break down this question. One is correlation of the series with itself, like with past legs. And you definitely, like, for example, if you look at the hourly time series that we looked, you probably see high correlation with leg 24 and leg 48. And then also, if you compare the weekly leg, which is 24 times 7, leg 168, you probably see that high correlation also there. So you should probably look and calculate enough legs to see that, because typically it won't give you until 168, but you want to calculate also the last, like the points that you think that there should be some correlation. In this case, you will see that you will have like a decay patterns over time with the different seasonal components. So leg 168, and then if you go and do the following week, probably there is going to be decay, right? So leg 366, and so on. And then you will have for 24 and leg 1, leg 24, leg 48, and so on. So that's you want to cover all the correlation with all the seasonal numbers. The second way is also, and it's a little more complex, is if you think there is the drivers, and for example, demand for electricity would be the temperature, right? You can take the temperature and check cross correlation with the temperature, and maybe identify it kind of like a lag effect. Maybe there is a delay of 1 hour between the rise in temperature that can indicate when my consumption will increase, or maybe it's just as it's happened. So it's with leg 0. And so, but the downside of using something like temperature is that if you are doing forecast, you need to forecast the temperature also. So you're training with actuals, but then you are using a forecast as input to your forecast, and that's adding some bias to your forecast. I hope this is a long answer for a short question. I hope this answered the question.
Thank you. And then the last one is for me, just a affirmation. For me, spectral analysis worked great for that purpose. Something like Fourier transformation.
Yes. So I was debating if to include the Fourier transformation, but I realized I decided we won't have time. There are other good methods out there that you can extract patterns. There is a Python library, and there is R implementation. I forgot the name. It's a Stumpy, if anyone familiar, which is running some metrics correlation. So it's a method based on metrics correlation that is kind of like trying to find relationship with like what are the best fit with the past variation of the series. I decided to focus on the one that are straightforward, and you should start with those that definitely, if you, there are much more advanced methods. Okay, if there are no other questions, can start to do forecasting. All right, so let's start by loading the libraries, load the data. So when using this function file, which just has some of the plots you saw before, I wrapped it in a function to not to create the whole code from scratch each time. And then we load the data from the our data file, and then we start with trend. So if you look at this time series, obviously there's no seasonality. And what we'll start with a better example to illustrate how trend is working, and then we'll see how to fix it. So make it a little bit more fun. So modeling trend is as simple as it sounds. We're going to add a trend component, which just adding index, right? So what I'm going to do is my series started in 1987, and I'm going to add an index starting with 1, and each time period that I'm progressing, in this case it's years, I'm increment this index by 1. And if you think about from regression perspective, if you are regress y against index, the output, the coefficient is the marginal increment of one time unit. So as you move at a one time unit, what is your delta? That's what it does, right? So like if we're moving from 2006 to 2007, you will get a constant that tell you how much you should progress. And so if this index, we start at 87, so at 19.7 should be equal 10, you multiply the index 10 by the value of this coefficient, and you get the value over here, and you need to add the alpha coefficient, right? So it's very simple. It's to create it. You are creating this sequential index, and now we're going to regress the trend against our dependent variable y, and we get intercept, right? And we get a trend, both statistical significant. You can see the R-square. We got a nice adjusted R-square, but in this case, it doesn't mean for the goodness of it, because if we will plot the fit So what we're going to do, we create a model. We now use the predict function and use this model and refit on the time series. So we're not predicting the future, we are doing a refit, get the values that the model saw on the training process. And we use, from interval perspective, prediction intervals, we use confidence interval. There are 3 methods that the predict LM function provides. One is confidence. The second one, which is relevant to forecast, is prediction. So because we're using the fit, we're going to use the confidence. If you are doing prediction for forecast, we will use the prediction. And then once we let's run it line by line, we will calculate, you get the fit. And the fit is essentially, you get what is the y hat, right, the prediction, and then you have a lower and an upper bound confidence intervals values. And we're going to assign it back to the data frame and going to plot it. So we got some line, and you can see, like, it's the thing about linear regression, that it will fit, like if you fit a linear line, it will optimize and try to find the spot right in the middle that minimize the error, right? Like any regression model. And one of the things that people, like, there is a misconception about linear regression. It's can only handle linear data, and it's not really true. It can handle nonlinear relationship. The linearity refers to the coefficient. The coefficient must be linear. You cannot multiply coefficient. You cannot have your beta 1 to the power of 2, right? It must be beta 1 times the coefficient plus beta 2 and so on. The variables, your independent variables, you can create like polynomial, right? That's a good example of a linear regression that fit nonlinear. So, but this is a very simple one, right? So you got a linear line, but you see that it's doing okay or not okay job, right, to fit. And we can look at the residual. So we're going to subtract the actuals from the fitted value and look at the values. And what you can see, there is some cycle, right? This is like yelling at you, like, there are some patterns left. Let's model them. And one way to see if there are patterns is to apply the ACF plot. So we use the plot ACF function to plot the residuals correlation. And as you can see, there is nice correlation on leg 1, which indicate that there are some information left over on your residuals. So this is where it's a good case to use a model called linear regression with a RIMA error, which essentially you add a RIMA component to capture residuals that left in your patterns that left in your residuals. And you don't need to have a RIMA, you can just add to this equation leg 1, right? If you progress, add to the trend and leg 1, you will take this like on the residuals. So let's say just go through the whole process of see also how bad is the forecast to understand when your fit value is not good, how it will impact your forecast. So to generate a forecast, you need one thing. You need to create a new data frame because we're using the predict method, and you need to provide a new data frame with the features that you build. So we're going to use, this is a nice function if you're working with Siebel, new data, which we are taking the time series that we forecast, the TS1, and we define what are the future values that we want to provide. So we say like we want 5 years ahead, right? So we set it as 5. Let's say we want to create 5 years forecast. And what it does is build the index with the future values. So our series is, where is it? Is ended at 2023. So now it's generating the next index for the next future. And now we just need to add the features. Since we use only trend, so we're going to calculate the trend. So if you look at the tail of the TS1, you can see that the last trend observation is 37. So technically we need to build it from 38 and so on. So we're going to calculate what should be the max value over here and add 1, and then calculate what should be the last value based on the horizon, so 5 years. So if we run this, and we leave trend start, so it starts in 38, right? We're adding 1 for this, and trend end should be 5 years. So it's 42, right? So let's add it to the trend, and now we can fit a line which will be our forecast. So we use the predict, and this time, because it's a prediction, we set the interval to prediction. We'll set to 95 prediction interval. So let's run this, and let's see, look at the object. Right, so we got 5 years or 5 observation, which is one represent the corresponding year. And then we got the lower and upper 95 prediction intervals for this fit. And we're going to add it back to the future data frame that we can plot it. So now let's rerun this. And you can see, right, so even if you look at the prediction intervals, probably if we have the future data frame, we'll be out, right? We're maybe touching the lower bound. So now let's think about how we can fix it. From feature perspective, we can see one thing that is happening here is that there is a change in the direction of the, maybe I will do it, right? So there is a change in the direction of the trend around 2008. So we're starting more or less going to this direction, and then from here, its slope is dropping a little bit down. So one way to model it is to use a method that's called piecewise linear trend, which essentially we are adding a second feature to the trend that it starts from 2008, and then regress it with the model, and we get the effect of like telling the model, look, there was some change over here, and let's adjust the trend from this point moving forward. You can add AR model, like autoregressive, or just regress it with leg in simple word. And you can do it both approaches, right? So this is the immediate things that we can apply. So let's see how piecewise linear trend will operate. So we think that somewhere around 2008 this is the point that the trend start to change. So we will add the starting point. We identify the time. So if I run this, the starting point. So it's what is the trend point that the trend change. So if I will do view TS1, so if I go to 22, so 2008, and it's represent this value. And we need this value because we're going to use the Pmax function, which essentially is saying we're going to subtract the trend with 22 and get the values that if it's less, it will be 0, and then otherwise it will start to increment from 1. So if I will calculate this, and we'll review the object again, it will be more clear how does the features look like. Right, so you see it 0 before 22 or starting from 23, and then start from here to increment 1, 2, 3, and so on, all the way to 15, which is the last observation. And now we're going to fit this model, and we regress with the trend and trend 2. And we get the 2 coefficients. Both of them are statistical significant, so it's good. And let's repeat the process. Okay, so now we see that there is adjustment and the fit change the slope from where we put the note, the 2008, and it's a by far better fit, right? And so if we will forecast this from this point, you will see that it's just continue this line. It's literally going to continue because it's a linear model, and we'll just keep the line in the same direction. But that's a very easy adjustment. And you saw like it's to generate those features is straightforward once you conceptually understand how they operated. Now, let's just add like I want to show it side by side. So I had those trend, the 2 trend, and together with the plot. So just to illustrate, right? So this feature, this is the regular trend. So you see we are incrementing by 1. And then we're adding the second feature that started from 2008, and that's the impact on the series. So it's really working nicely in this type of scenario. And if we go and review the residuals, we can see that compared to the previous one, the range is lower. Like if we go back to the previous residual plot, so you see here it's ranging from plus 300K to minus 300K, as opposed to still like there's some patterns, but like you see, it's now much more centered around the 0. Maybe there are some outliers, and those outliers may be related to some fluctuation that, you have this, something happen here, right? Something also here. So you cannot win it all, but at least like I think in forecasting, you need to get the trend right. If you don't get the trend right, if you get the seasonality, you get the other, your forecast is going to be not as good, because the trend is is the backbone of your forecast. Okay. So, so we saw this method. Now let's look at a different method. And we saw the piecewise, very useful. And now think about like if you have more than one dump or change in the slope of the trend, you can apply multiple of those features, right? So not limit to one. You can have more. Okay, and I think, and we can see if we look at the residual before we move to the next method, the correlation, you can see there is still like leftover. Now it's less significant, right? So it's still maybe worth checking. It's 0.66, but you don't. Most of those are out of the, are not statistically significant, and you should not be too worried if you sometimes you will see like some random legs that are still have some correlation, maybe it's low and statistically significant. You also don't want to overfit, but maybe yes, we want to add here also leg together with the piecewise, and we might improve this model. So we saw piecewise. Now let's look at AR. So we're going to add, essentially, we're going to build from scratch what is called linear regression with ARIMA error. And the ARIMA component is the AR, the auto-regressor. We're going to edit manually. And we will create, so from feature perspective, we need to create leg 1. So this is what I don't like in table. I decide for you what it's showing and what is not. So I need to. Okay, so you see leg 1. Okay, so the value of the series is starting here in 1987. It's a 7,904,000,000, and in 88 it will move it, shift it, so that will be leg 1. So essentially what we're going to do is to regress this against this, right? Because we're assuming that the previous observation has a lot of information about impact on the next one. So we're moving it in a tabular format. We're just using leg 1, and we're going to use the leg with the trend. So you see the regression model here. We are regressing Y against trend and leg 1, and let's see the model. And one thing to notice that when you're using leg, it remove the trend. It's not statistically significant. And the reason that, because both of them are covering probably the same, so it's masking the impact of the trend. So you may consider, like, if you run like a step, I think it's the step function on this model, it will drop the trend and just leave the lane. So that's something that if you have many features, you can check the step function. That is essentially, if you're not familiar with the step function, it's running a stepwise regression, a stepwise algorithm that essentially it's calculating for each combination of features what is the AIC score or BIC, depending on what you define. Trying to see here, AIC, I think there is also options to do BIC, or it's only AIC. And based on the score, it's identify if this feature is relevant or not. And if not, it will remove. The only caveat for this approach is this algorithm is selfish in a sense that it will run in a certain order, that if you see opportunity, it will remove the variable. But if you will try a different combination with a different order, it might get eventually better results. So this, like other algorithm that they going in one direction and they don't validate different direction, you may sometimes lose some variables. So that's if you have a lot of variables, you should be concerned. But for now, let's just keep this model and see the fit. And you see, if we're looking at the correlation, that's it, no correlation left. So you know that your residuals are now clean, nothing left, you're done. In a sense, like this model is now, should be robust, right? One thing that that worth to mention on residuals, there are, when we look at the residuals, we are looking at 3 plots. One is the residual plot that we just looked at before. The second one is the correlation. Third one, we are plotting the distribution. What we want to see that the residuals are normally distributed, and the reason is this is one of the assumptions of the prediction interval. So if your residuals are not normally distributed, the assumption about the validation of the prediction intervals are not valid, and then you might not be, you're violating the calculation, like the validation of this approach. Okay, one thing to caveat about legs. When you're using legs, you need, when you're doing forecasting, and I didn't create the forecast, but if you are creating a forecast with legs, you need to supply the future values. Now, if you're using, for example, in this case, leg 1, and you're doing a forecast of 5 years, so for the first observation, you should be good. You will have leg 1. You are the last observation on your time series. But then for the second observation, you need to recursively calculate the value for leg 1 for the second forecast that you want to do. And so in this case, you're not using actuals. You start to use a prediction. You use the forecast for the first observation. So you are adding some bias to the model. Now, there are ways to work around it. Like, so if you're, and I'm not covering today because of time, how to train time series with backtesting and other approaches. But if you are splitting into training and testing, you need to think about on your testing to run the exact same method that you will calculate the forecast. So if you need to produce the legs in the forecast, so also by creating like using the fitted value, do it also for your testing. Because otherwise what will happen, you will use the actual values and it's going to create some leakage of information, or it's not leakage of information in this case, but it's you don't have the bias that you will have in your forecast. So if you want really to measure your forecast on testing in the exact same scenario, you should use the predicted value. And this is the case if your legs are the size of the leg, like if leg 1, for example, is smaller than the horizon of the forecast. I said that if I use leg 12, in this case, for leg 12, and I'm using only 12 months, I should be good. I can only use actuals. But if I'm doing 24 months of forecast, so then from the 13th forecast, I will start to use leg 1. Sorry, the first forecast. Might be confusing, but this is where you need to create a recursive function to generate it on the fly. So now we go to the last topic, which is modeling seasonal time series. So by going back to the monthly consumption of natural gas, obviously, in this case, you have a single time seasonality, right? You can see nicely the variation is driven by the month of the year, where January is peak. And let's repeat the decomposition using STL. So we're going to calculate the STL for this and plot it. So we see it's very clear. So you have a trend. There is something here happening. We will touch it in a second. And then we have some outliers. So now what we want to show, how to handle seasonality. And then we want to address this shift over here. And lastly, we're going to touch the outliers. Okay. So again, let's generate the trend feature, right? So again, we're going to use this same approach. We're going to index the series from 1. And then if you run just with there was a question about detrending or stationary, making the series stationary. And this is what we're going to do. So we start with just regressing the model with just trend. Now, one thing to notice that the R square here is very low because only by trend, it's not really expanding. And if we plot it, you can see, right? So we more or less in the middle, but if you look at the residuals, let's see if I have the plot. Let's plot the residuals. So if I want to plot the residuals, I need to, let's take the previous. Let's do it on the fly. So we have, let's call it TS2, and let's call it residual 1. And so we are subtracting from the actuals the fitted value. So we call it TS2 and fit 1, right? So we are taking what we fit over here, and we're subtracting it from the actuals, and then we want to plot it. Oh, that's the ACF. I think I have it later. So let's just continue and I will return for it. I think I already created a plot. So we want to add a seasonal component. And here, because the month of the year is the seasonal component, so we're going to generate a variable called month. And we use from the lubridate the month function. Essentially what it does, it's adding a categorical variable with the month of the year. Now, in R, when you use the lm function, when you apply on a categorical variable, what it does on the backend is apply autoencoding. So you don't need to calculate the autoencoding. It will automatically generate the autoencoding. So we use a categorical variable, and on the backend, essentially, R is doing the lm function is doing the autoencoding for us. And now if we will run it together, you can see that adding the seasonal component, our adjusted R square is now jumped from 0.3 to 0.92, which is good. And most of those are statistically significant. And let's plot it. Right, so now the fit is, and this is again like, you can do fit of nonlinear data with linear regression, right? So it's not that a problem. We got a fit. We see that we are okay-ish, right? Still we can improve, right? We may be missing some of those. We have the outliers that we talked before. We have this is a huge outlier. We have a linear growth, right? It might be not the case. So let's address those things, right? So you see by the shape of it that we have a lot of the residuals are big in the start. We are center right in the middle, and we are up again. They're going up or positively up toward the end. This is the characteristic of linear regression. That linear regression will be, if you take the x and y axis, the average, it will be centered around the average. So that's why around the middle of the series, it will be more close, and then on the tails, you will have high residuals. So let's help this. Right, so going back to our residuals plot, you can see one that you have still like seasonal component left in the residual. So there is some, maybe leg 12. And leg 1 is still high. For example, here, I would ignore it, right? It's some relationship with leg 49. Maybe it's a 48 because of it's a seasonal, but I would ignore it. You should not be as take with grant or so, like if you have like those that are not as outside of the bound of the confidence intervals. This is something you should think about. I have some opportunity. So let's go to see how can we improve. So if we go back to, I find it. There is a structural break here, and structural break in time series is when you have some level shift of your time series either up or down. A good example is during the COVID pandemic. There was an abrupt shift in some microeconomic time series, right? So the unemployment suddenly in the US went up, skyrocketing, right? And then, like, if you look at passenger travel, flights and passenger travels, there was a shift down. So you see there is a level shift, and then from after this level shift, you're continuing the same, more or less as before, the same slope. So we want to add this factor as a feature. How do you add level shift? Very simple. You create a feature that is, let's say if we think that the level shift is somewhere around September 2018, you create a new feature, a column, that is 0 before and 1 after. Right, so that's the model is learning to break the weight between before and after, and help the model to adjust the trend. So we'll go and create this structural break by setting any observation after September 2018 as 1, as 0 before. And create table Q1, right? You see it all the way in the end, right? So it started with 0, and then this is the tail of the time series, it's 1. And now we're adding this to the regression, so the structural break with the trend and demand. And the structural break is also statistical significant, so it's good indication. And we can replot. Right, so you see that we apply the structural break over here. So now it's lifted a little bit, and it's capturing, you can say it's capturing a little bit better. You still may be missing over here. But overall, the trend is now more aligned to the series. So one of the things that we saw before that there was higher residuals on the tails, and now it seems like more statistics. I always challenge with this word, statistic, but you know, if you did some statistic, it spread really nice and evenly as much as it can. So let's see how we can focus it. So I think we're in a good shape now. Let's generate a forecast. So I'm creating a feature table. I'm adding the features. I need to create all the features that we use. And I'm running the predict function. I'm providing the new data frame. And then I'm adding back to the future data frame the forecast with the prediction intervals. And now let's plot it. All right, so now we have forecast. It seems like okay. One thing that now we want to handle, and that's the last thing because we are 5 minutes before the time, is that we want to address those spikes and see, you know, if we improve the fit. One thing that you should worry about spikes going back to linear regression fit in a way to think about it as a scale. Linear regression fit exactly in the middle of the y average of the y and the x. It's moving right in the middle. No matter what you do, it's balanced around if you average the x and y, it will cross this point of the intersection between the mean of x and mean of y. Now, if you have points that are on this quarter of, if you create like a imaginary quarter and you have points that pushing it up, it will push the slope up toward up and take it out of balance. And you want to remove the effects of these points to make the slope or the trend a little bit better. And similar, like if you have point down over here, they will shift up and it will be the inverse effect on this area or on this area. So we want to take from the regression, the weight on the seasonality of those points. So you can think about, like, if we look at eyeballing this, you can say that, this is those outliers have the same kind of like a weight, and this is maybe a stronger impact of outliers. So we can segment this as a one outlier, and the rest 5 points, January 14, 18, and so on, as a medium outlier. So we will create a feature for those one and a separate feature for this one. And the way to do it is generate a new feature, and let's see the feature, which is zero. It's zero. Oh, Tiba is like annoying. All right, so you see that we created those 2 outliers. They are 0 on any point besides the dates that we define, right? So if I do the table, right? So there is one point that we marked as 1, and probably if we'll do the tail, it's the last points for, you see here, that's the point, right? Corresponding to January 2025. And then similar, we'll have the corresponding dates for this, the medium outlier as 1 and 0 elsewhere. So now when we add this to the model, you can see that, again, all the variables are statistically significant. And if we plot it, you can see now that the fit is better. And essentially what you want to, the concern is, like, you want to remove the weight of those outliers on the trend. So that's what the goal. One thing that now we don't have time to cover, but like I will say, like, how can you, in this type of time series that obviously the impact is derived from external factor, by the weather. Now I don't think anyone can tell what would be the winter in 4 years from now, let's say, if you want to do a forecast. One way to address it when we don't know is to create scenarios and apply simulation. So if we want to, let's say, forecast the next 5 years, and we want to do some simulation, we can come with some assumption about the distribution of event and do some sampling and run many times this sampling and simulate different paths that with those events and without, and then extract some kind of like this simulation and calculate some mean or median, and come with some range of options, which is more probabilistic other than deterministic. And I will pause here and see if there are any questions.
Thank you very much. That was great. I learned a lot. So I'm afraid we're short in time, but I think people has appreciated all your explanation. Thank you very much. I don't know if there's any question. You can unmute yourself. We just have like 10 minutes left, so please feel free to unmute yourself. In the meantime, we have a flow of thank yous, thank you very much, and so on and so forth.
I would say that if you are looking for a good resource, let me, this is one of my favorite, is Rob Inman book. It's free and open.
Yeah, I
put
love
it in the
that.
chat. It's a good place to start.
Yeah. Yeah, but let me say that I appreciated because you went inside the functions. So you show us how to make the things, and then obviously you can use the already made functions. Once you know the background and everything, you can trust the output and things.
Yeah.
So yeah.
Once you understand conceptually how does features work, you know the sky's the limit. You can then, if you want to apply different regression method, you can use different regression method. The nice thing about linear regression that for most cases, when you have a simple, like the data is not big, it's low, cheap on compute, and fairly do good work on prediction. So it's always a good option to start with, like prototype, and then if you want to, maybe the cases that you may want to use a different method, when you have a lot of features and then you want a more robust method to do feature selection. So those all the three models, they are good in feature selection, region, raster regression, and so on.
Well, thank you very much. If there's no any other questions, I think we can close this workshop. And thanks again, Rami, Krispin, for this insightful session. Thank you very much for staying with us, for all your thorough explanations. So
thank you so much for the invite.
Yeah, thank you for accepting our invitation, to be honest. And so thanks for your time and everything. Stay tuned because we are going to post the recording on our YouTube channel, youtube.com/@rladies.rom. And so we will make a post and everything. So a blog post with all insights and materials of this talk. Thank you very much. And I look forward to see you very soon, actually, because we have another event on the 22nd of July, and that will be in Italian, entirely an Italian event about data visualizations with Rita Giordano. So stay tuned, and thank you very much for being with us today.